Hello and welcome to a new geometry gem. On this gem, what we're going to do is we're going to implement a polyline simplification algorithm. It's called the Ramer-Douglas-Peucker algorithm. And let me show you how it's going to look. I have here a polyline. I have a curve that I have subdivided in 200 elements. So I have a polyline that has a lot of tiny, tiny elements between vertices that are very close to each other. But with this algorithm, I can set a threshold distance that I'm going to use to define which vertices are not really giving me any information or any meaningful detail for this polyline and which ones are important for the overall shape. So as I make that distance a bit larger, you can see that the polyline starts simplifying, but altogether, overall, it kind of keeps the overall spirit of the general shape. So this algorithm is really good for simplifying points that are not really adding a lot of detail or that are like almost like tangent to the polyline at certain times. So you can see how detail starts popping up on the curves, on the curvature, as opposed to the more straight line segments, you know? So this is a super, super useful algorithm to simplify, for example, drawing strokes or to simplify trajectories for drones or for robots. And it's also a very nice one to implement just geometrically. It's also very easy to implement conceptually. And actually, full disclaimer, this implementation that we're going to see here is not at all one of the most performative or one of the fastest ones. But I believe it's one of the ones that is easier to understand, so it has educational value. But if you're looking for a performance implementation, then perhaps this is not where you're going to, where you want to look. You want to look for an algorithm to learn exactly how this works. I'm going to be implementing this in Grasshopper for Rhino, which is a parametric modeling environment connected to a 3D modeling environment that allows me to do C# scripting. I'm going to use this environment because it gives me a lot of visualization capacities out of the blue, with very little effort. And as you can see, you will see that in this code, I'm almost not using any of the libraries that come with Grasshopper. So you will be able to take this code and replicate it in any other C# based environment, like for example, Unity, VVV, or Mac, you name it. Okay, so follow me and let's get busy and let's implement some cool simplification algorithms. Let's talk a little bit more in detail about what we're going to be doing. What we're going to implement is called the Ramer-Douglas-Peucker algorithm. I hope I pronounced that well. I'm really bad with names in English. And this algorithm is a really nice algorithm that is designed for polyline simplification. It's commonly referred to as the Douglas-Peucker because I believe that historically the two authors came up with the idea simultaneously, right at the same time, but without talking to each other. And they actually got their papers published on the same journal, on the same edition, back to back, one after the other. So it's kind of unfair to attribute it one to one or the other. But it's a really simple algorithm, which is very interesting because it's a very nice way of simplifying a polyline. Because, for example, imagine a polyline and imagine that the polyline has 100 points, right? We can come up with a lot of simple rules to simplify that polyline. Like, for example, why don't we just eliminate every other vertex, right? And then we end up with roughly half of them. But the problem with such simple approaches is that, for example, if the polyline has like more of like a convoluted geometry on some edges and less density of points in others, then maybe the overall shape of the polyline with such simplification would get very distorted, and we will be keeping points that are not really adding detail to the polyline, and we will be pruning out other ones that actually contribute to the overall shape. So the nice thing about this algorithm is that it does a really good job at sort of maintaining the overall high level shape of the polyline while simplifying the points that are not really adding much detail or they're not really contributing much to the overall shape. So and also fairly easy to implement. So what I mean with this overall shape, like, is in this curve that you can see here, you can see how the overall shape is basically an undulation that keeps damping down. So the algorithm is actually smart enough to be able to identify which are the vertices that actually represent the spirit of this polyline, and then keep those, as opposed to the other ones, for example, all the vertices that would be in the middle of this like almost straight line, which are not really adding much detail to the polyline. But how does this algorithm work? So it's actually very interesting because it's also a recursive algorithm, which I will explain more in detail what that means. But the process basically goes like this. We start off a polyline like this one, and then what we do, and we start off also from a distance parameter that we call the epsilon. And that distance parameter is going to be sort of the value that we use to control how defined we want the curve to be, the polyline to be. And how it works is like we start by taking the endpoints and figuring out which one is the point that is farther away from this initial straight line. And once we have that point, if that point is outside of this epsilon range, so let me show the diagram again. So you see the line, and this point is farther away from distance epsilon, then that point will be kept. However, if like we have here, if the point is inside of that epsilon distance, so if the distance of the point to that line is less than the epsilon value that we are setting, then it means that that vertex will go away from the polyline. The result of that is what you're seeing here. This polyline gets simplified. This one, and this vertex, they all go because you can see intuitively that they're not really adding much detail to the overall shape of the polyline, which I think it's a really interesting and a really smart way. Why are we going to do this? We're going to do this because polyline simplification is actually a technique that is very common and very useful in many different fields. So for example, if you're doing robotics and you send a very complex polyline for the robot to follow that has thousands of points, then the robot may actually not be able to take all of that, and simplifying it in a way that still maintains the overall trajectory of the robot is a very useful thing to do. It's also very useful, for example, when you want to simplify diagrams that are made of tons and tons of polylines, but you want to keep the overall shape of the sketch, for example, if you're drawing, So it's a really useful technique, and also it's a very nice algorithm to implement because it's not very hard. So we're gonna see how to do that. So actually, before we start any coding whatsoever, I would like to spend some time in the whiteboard and then break down the step by step the process that we're going to follow. Okay, so let me draw some stuff and let's explain stepwise what we're going to be doing to implement this algorithm. All right, so let's talk about algorithm. Whenever you design an algorithm, this is a super important thing that you need to do before writing any code. You need to sit down and sketch what you're going to do, and then go and do it. Okay. So you always think before writing any single line of code. Otherwise, your life is going to be a nightmare. I can tell you by experience. So here I just drew a polyline that has 7 vertices. Remember that in computation we usually start counting by 0 and we end up whatever the number of vertices minus 1. Okay. And then how the algorithm works is the following. The first thing that we do is we are going to draw a straight line between the first point and the last point. We always start between the 2 end points of a polyline. All right. Now that we have that, I'm just going to draw this band of sorts, which is going to represent. Which is going to represent, and this distance here. This distance here is going to be epsilon. Okay. What does that mean? It means that all the points that once we have chosen the first one and the last one, what we want to do is we want to calculate all the points in between, which one is the one that is the farthest away. So what we do is, for this particular case, it's very easy to see that the farthest away would be point number 3, okay? And because we see that this distance here is much larger than epsilon, which is the value that we're using for the precision of the polyline, then what we have to do is we have to follow a recursive process where what we're going to do now is we're going to subdivide our polyline in 2 chunks. Okay, so one of them is going to be the beginning of the polyline and that vertex that we just chose, and the other one is going to be the vertex that we just chose and the other end of the polyline. Okay, what does that mean? What we do now is we say, well, we're going to apply the exact same logic to those 2 independent chunks. So we're going to assume that this here is now our polyline, the one that we want to simplify, and then we're going to operate the same thing. We're going to calculate which one is the farthest away, and this one is going to be if we draw this diagram, we're going to assume, if we draw this diagram, we assume that this one is outside of epsilon, and because it's outside of epsilon, then we actually now forget about it's outside of epsilon. So now we take the polyline that we had and we subdivide it in this polyline and this polyline. Okay, and doing this, now we can see that if for this polyline we calculate the farthest point, which is obviously this one, and if this one is included in the distance epsilon, then we remove this point. So this one, this segment now becomes a permanent segment. Now becomes a permanent segment of our final geometry. This one here. For the second one, between 2 and 3, because there's no points left in between, we're going to also include this here. And now we go back to the other one that we had on the far right. We also do the same thing. We calculate whether if any of these points, so this point here and this point here, if any of them, which one is the farthest away, and we can see that in this case is number 4. And if it just so happens that all the points, that the point that is farthest away is inside of epsilon, so if the distance of that point to the line is less than epsilon, then because it was the one that was farthest away from all the points, then we can see that that whole segment is a segment that can be simplified by removing all the vertices in that particular segment of the polyline. Because if the one that was farthest away is still less than epsilon, then all the other vertices are going to be also inside of epsilon. So what that means is that the simplification here is now very clear. I can remove this and I can say this is going to be part of my final polyline. And you can see that this is the process. You can see that this polyline that had 7 vertices, we have removed 3. So now it has 4 vertices. Let me draw like a thicker line here. 1, 2, and 3. Okay, and that's the simplification. What's interesting about this is that we have applied a recursive logic. We started with, let's simplify the whole polyline, but we found a vertex that was outside of epsilon, so we divided the polyline in 2 segments, and then we said, okay, let's now simplify the left part, and then we will simplify the right part. The left part, oh, we also had one that was outside of epsilon. Okay, so then let's subdivide that in 2 more polylines and apply simplification to each one of them, and so on and so on. So you can see how we're going to create like a tree or recursive operations until we reach a point where the polyline can be simplified and all the vertices can go, or we reach a situation where the polyline only has the start and the end points and there's no simplification to be made, in which case we don't keep going farther down. All right, that is the idea of a recursive algorithm, which is a very common technique in computer science. All right. So how about we start writing some code and make this happen, huh? So let's get started. What you see here is that I really quickly put together a very simple polyline. So what I did was I created like a bunch of points here in Rhino, and then I brought them into Grasshopper with a parameter component. And then just for the sake of visualization, I joined them with a polyline. And then I also added this point list so that I know their indices, which will be very useful in very soon when we start debugging the code that we're going to be writing. I want to make something very clear, and I would like you to think of polylines. I would like you to think of polylines not as segments that are moving in like a saw kind of shape, but actually a polyline is nothing more and nothing less than an ordered list of points. So I actually don't care at all about lines or segments, whatever. I care about the XYZ coordinates of each one of the points that are part of this polyline. So for my C# script component, I'm actually not going to take I'm not going to take a curve, or I'm not going to take a polyline object. What I'm going to take is point 3Ds, and I'm going to take them as lists. This is very important because I want to have a full list of all the points one after the other. Epsilon is going to be the value of type double, and I'm just going to plug in here some slider with a lot of precision, and I'm going to use this to control that distance that I was talking about before. And then I think at this point we are ready to start writing some code. And the first thing that we're going to do probably is we're going to start with the first round where we compute the distance of all these points to the first line segment that we're going to create between the start and the end points. Before we start, it's going to be very important for this algorithm that we have a way of calculating the distance of a point to the line that is formed by two other points. And I have a geometry gem that I recorded where I explain how to do this, and I wrote the algorithms. So there was probably going to pop up a link somewhere here, or you can find it in the description. But so I copy-pasted some of this code. I copy-pasted a function that, given a point P, computes the distance of that point to the line formed by two other points A and B. And because this implementation is using the cross product, I'm also copying here an example of how to write the cross product of two vectors. I am using C# scripting within Grasshopper, so I could access the Rhino Common API to do this. But if you're trying to write this on a different C# environment, then this implementation it will be super easy to copy and paste it between different implementations. Okay. All right, so I think we're ready to start writing some code. The first thing that I would like to do is I'm going to, instead of writing everything here in the main code, because this algorithm is going to be recursive, it's very important that I write a function that takes a list of points and an epsilon value and returns a simplified list of those points, because I will be calling that function recursively on top of itself over and over. So I'm going to do that here. I'm going to create a function, and I'm going to call it simplify polyline. This function is going to take a list of point 3D objects, for example, points, and it's going to take a double value called epsilon. And the return type of this function is going to be also a list of points, because it takes a list of points but returns a simplified list of those points. And I'm going to start real quick by returning null so that I can see that if I run this, I don't get any errors. And I'm going to write here very quick that the result of this outcome, so the result is going to be simplify all those points and the input using the epsilon value that we have as an input for this grasshopper component. Okay, so this function is now an empty function that does absolutely nothing, and you can see here that it gives me no data whatsoever, but it also doesn't give me any errors. Okay, so we are at a good position to start writing some code here. And the first thing that I would like to write is the first part of the algorithm is let's take the start point, the end point, and then let's calculate the distance of each one of these values, each one of these points, to the line formed by these two vertices. Okay, so that's very simple to do. So for example, I can do that with a for loop where I say I is less than I. It's going to start with 1, okay? Because here I don't want to start with because if the start point is point number 0 and the last one is point number 7, the first one that I want to check is point number 1, 2, 3 all the way up to 6. So that's why this for loop, where did it go? Oh, okay, I don't know where that went. So I'm just gonna write it again. So I can start with a for loop that starts at the value of 1. I is going to be less than however many elements are in this polyline minus 2. So for example, I have to go from 1 to 6. There are 8 vertices in this polyline, so the last one is going to be 8 minus 2. So it's going to be points dot count minus 2, and then I plus plus. And then for each one of this, I'm going to calculate the distance, double D, the distance between that point and the start and the end point, the line formed by the start of the end point. So that's going to be distance to line, and the point that I'm going to check is points I, so each one of those points in the middle of the polyline, and then the points at the ends, A and B, are going to be points 0, the first one, and points dot length minus 1, which is going to be the last one of the polyline. So I'm going to print this to the console just to make sure that things are working correctly. And I got an error. That's very common. So number 66, yes, I use points. I use PTS, which is the value of the points on the component, but it's not the value that we see here on the function. So I'm going to replace that. And then I am using length, which is only for arrays. I should use count. And then 68 print. Okay, so I'm going to print this distance, and you can see that I have 5 distances, 1, 2, 3, 4, 5. Oh, that's not, something is not going well here. So 1, 2, 3, 4, 5, 6. Oh, because it should be less or equal than point minus. So it should be, yeah, so this is minus 1, okay? So let's see if this works. So if we have a line from 0 to 7, this point 18 units, this point is less 10 units, this point is 45, a lot very far away, 32, 36, those two are close, and 20. It kind of looks like it's working because it looks like 3 is the one that is farthest away from this line. So we are good. Okay, so that's a good start. The next thing we need to do is we need to figure out which one of these is the one that is farthest away. That is very easy to do. In this algorithm, we can keep track, outside of the for loop, we can keep track of the maximum value that we do by initializing 2 variables. I'm going to initialize a variable called maximum distance, which is going to be the variable that I'm going to use to keep track of the maximum distance that I have found over all these points. And I'm going to initialize it to a ridiculous value, like for example, minus 1. You cannot have a distance of minus 1. So So because it's so small, every single value that we find distance is going to increment this. This is a very common technique to do. And I'm going to also initialize an integer maximum index, which I'm going to use to keep track of whenever I find a point whose distance is larger to the line than any one that I have found before. I want to keep track of which one that was. Was it 0.1? Was it 0.3? 0.7? So I'm going to use this integer maximum index to keep track of the index of the point that I find with the maximum distance. And I'm also going to initialize it to a value that is ridiculous, -1. We cannot have a point on a list with an index of -1. That is just not possible. So because that's the case, then it will be helpful for us to identify if we have found such a point or not, etc. Right? And then here, what I'm going to do is I'm going to say double D equals the distance. And if the distance that I found for this point that I'm checking in the for loop, if this distance is greater than maximum distance, so if it's greater than any other distance that I have seen before, then turn maximum distance into that value. So if the largest value was 25 and now I have 40, then now my largest value should be 40. So maximum distance is now the value of the distance that I just found. And then the value of maximum index is the index of the point that I am checking right now. Is that okay? Let's see if that works. I'm going to print here index, maximum index is going to be equal to I, and then maximum distance is going to be equal to max dist. And I have a typo here. This is not I, is maximum index. Let's see if this runs. I'm going to close this here, and it looks like this is working well. It looks from my polyline that number 3 is the vertex that is farthest away, and that 45 is the distance between this point and the virtual line between 0 and 7. So we're on good track. Okay. What is the next thing we're going to do? If you remember from when I described the algorithm, there's two things that can happen when we find the point that is farthest away from that line between the endpoints of the polyline. If that point is inside of the value of epsilon, then if that point is outside, then we have to start subdividing the polyline and applying the same logic to the two ends of the polyline. That is a little more involved. We will do that last. But then if it's not, if that point that is farther away is the distance is less than epsilon, then that means that that point should also be removed because their distances are also going to be smaller than epsilon. Okay, so that one is a bit easier to do. So after what I wrote here, here I already know for this segment of polyline which is the point that is farthest away and how far away it is. So what I'm going to do here is I'm going to write a very simple conditional, and I'm going to say if maximum distance of this point is greater than epsilon, then here I would have to do recursion, and I would have to divide the polyline and then analyze the two segments independently. Otherwise, if it's not, then what I need to points, I'm going to write it here. Do subdivide poly and apply recursion. And then otherwise, just remove all points between endpoints and return. Okay, so let's do that. Oh, sorry, I forgot I was not. Yes, thank you. So I'm going to write a very simple conditional where I say if the maximum distance is greater than epsilon, then please subdivide the polyline and apply recursion to the two ends. But otherwise, if it's not, then just remove all the points between the start point and the end point of the polyline. Okay, so this is going to be easier, so we're going to do this here. Before I decide what to do with each one of them, I'm going to create an empty list here, which is going to be clean points, and that I'm going to not even initialize here. And what I'm going to do is, here I'm going to write some placeholder text like should do subdivision here, and then here I'm going to initialize this list to just a new empty list. Just a new empty list. And here, what I'm going to do is I'm going to create I'm going to write, I'm going to say for the polyline that I had, I'm going to keep only the first point and the last point, and that is the list of clean points that I need to return. So clean points is going to be equal to a new list of point 3D objects, okay, that I can initialize, and I'm going to initialize it with 2 points. One of them is going to be the first one on the list, and the other one is going to be the last one on the list. So it's going to be points.count minus 1. And I'm not sure if you're familiar with this kind of syntax. This is C# syntax for creating a new empty list of point3D objects and then giving it some initial values. So 0 and the last point. Let me see if this works. This works, yes. And then what I'm going to do is I'm going to return from this function, I'm going to return the list of clean points, which either has something for the subdivision or that has this clean polyline only with the first part and the end part. So let me see if this works. So I'm going to execute this. You can see that that epsilon is right now at the value of 10, and you can see that here it says, oh, the maximum distance is 45, is greater than 10, so I should do some recursion. But if I crank this up all the way up to above 45, then what should happen is that all of a sudden I should be getting the output, which is just the first point and the last point. Let me add a polyline component here just to make sure that exactly. And because this, in a way, is the simplest form of simplifying this polyline, just the very beginning and the very end of this polyline. So this is a good beginning. So now let's see how can we split the polyline in two and then apply recursion and apply this logic to each one of the two ends. So follow me on this one. Before we go any further, I want to go back to the writing board, to the whiteboard, because I want to explain how we're going to do this. Remember that imagine we have decided that we have found out that vertex number 2 is the one, this one here, right here. I can touch you. The one right here is the one that is farthest away from the line between vertex 0 and vertex 6, all the way up there. So what we need to do now is we need to divide the polyline in two parts, and splitting it by this one here, and then perform simplification on this one, the polyline between 0, 1, 2, and then perform simplification also on the polyline 2, 3, 4, 5, 6. Okay? Therefore, and then apply the same logic, but to those separate, to those two separate polylines. And then once those have been simplified, then we will mix them together and into the simplified polyline. And in order to do that, what I would like to do is I'm going to go back to my code, and then I'm going to say here, whenever I subdivide the polyline and apply recursion, let's start by doing the following. What I'm going to do is I'm going to create, because remember, polylines are not really polylines, are just list of points. So what I need to do is I need to create a list of points that contains point number 0, number 1, and number 2. So what I'm going to do there is I'm going to say point 3D, I'm going to say left poly, okay, is going to be equal to a new list. It's going to be equal to a list that has all the vertices starting from 0 to number 2. So how does that work? I have all the points of the polyline here. So lists in C# have a property that is called getRange, and getRange gives me a certain subset of the points in that list. And the way this works is that the first parameter is the starting index of the element that I want to grab. So in this case, because we're taking the left chunk, the first one is going to be 0. And then how many elements do I want to grab? Okay. In this case, if you remember, let's say the index of the vertex that we want to pick up is vertex number 2. So if we want to start at 0 and we know that the vertex that we want to stop at is number 2, we know that we need to take 3 vertices, which means that what this means is that if I know the index of the vertex that I want to take, I want to take that vertex plus 1. So you see here, vertex number 2, I want to take 3 vertices. Starting at 0, I want to take 0, 1, and 2. So that's how we're going to simplify and take the left chunk of this polyline. But now I also want to do the same and then pick up the right part of this polyline. Okay, and how are we going to do this? Well, we're going to do a similar thing. We're going to use getRange, and now we want to start with the first vertex being the one that we know is the farthest one away. So we're going to do max index, and then we need to calculate how many vertices do we need to take. And in this case, remember this polyline that I have drawn here has 7 vertices, and you can see if you count that we want to get 5 vertices. We want to take 2, 3, 4, 5, and 6. What that means is that the number of vertices that I want to take is, starting with number 2, I want to take the amount of elements that are in this polyline, in this case 7, minus the index of the vertex that I want to pick, in this case 2. Because I want to take 5, I want to take 7, the total, minus 2, the index. So that's what points dot count minus maximum index. Okay, let me check that is correct. Is this working? It is not. Oh yeah, well, it's not working for a different reason. So here is telling me that I'm using an unassigned. So for that error to go away, I need to create at least an empty list here. But everything else is working well. Is it though? Yes. If I go down, this doesn't give me any error or like out of index, blah, blah, blah. Okay, so I have the left polyline. And now what I can do is I can actually do recursion. So divide poly in 2 parts, the left and the right. And now apply recursion to each one. So what I'm going to do is now I have a smaller polyline, the left polyline, which is just 3 vertices. So I'm going to apply recursion to that polyline. And what I'm going to do is, remember I am on the simplify polyline function. So what I'm going to do is I'm actually going to call this function again from within itself. That's exactly the concept of recursion. It is, I am on a function that is going to call itself to perform like a subset of its operation, that is going to call itself to perform another subset of the operation, etc., until we hit one of those limits that we were talking about before. So I'm going to say, I want to simplify now the left poly, and I want to use the same epsilon that I've been using before. Okay? And this function is going to give me, as a return, is going to give me a list of points that has been simplified. So I'm going to do something like this, and I'm going to say the result of that simplification, I'm going to store it in a variable that I'm going to call left simplified, for example. And I'm going to do similarly, I'm going to do the same with the right end. I'm going to say right simplified is going to be simplify polyline and right poly. Is this clear? I'm taking the two ends, the two polylines that I created, and which have less vertices, and each one of those, I'm also going to apply a simplify polyline to each one of those two ends. Okay? And I'm going to store those two results here. I just want to make this process very clear again. If I go back to the diagram, you can see that we have divided the polyline in two. Okay? What's going to happen probably is that now I'm calling simplify polyline on this segment. And what's very likely to happen is that number one is going to be very close to the polyline. So what that means is that when we call this function simplify polyline on the left end, we're going to start over here again, but we're probably going to end up here because the maximum distance is probably not going to be greater than epsilon. So you're going to see that this is going to immediately return a list of clean points that only contains 0 and 2. And therefore, we're done on this branch of the calculation, on this branch of the recursion. But on this branch of the recursion, there's probably going to be even more recursion going on here, because as I do this end here, you can see that probably I will end up splitting on vertex number 3, and I will have to apply recursion to this segment here and apply recursion to this segment here and simplify those two independently. So you can see how recursion starts branching down and it starts creating operations that are like atomizing the simplification until we hit a limit where there's no more possible simplification to be done. And therefore, we return a list of clean points, and then we start tracing back all of our recursions until everything starts mounting back together. So let's keep going. And now the last step. The last step is we have split the polyline in two. Each one of those two gets simplified down the tree recursively. But then, assuming these two branches of the polyline have been simplified, we need to reunite them somehow and then return them as part of this function. So we need to take the left part that has been simplified and the right part that has been simplified, put them together as a list again, and then that will become the simplified polyline. So that's actually fairly easy to do. So what we can do is we can say the clean points, I'm going to remove this now. The clean points list that we want is going to start with the points that have been simplified on the left part. So left simplified, okay? And after that, I'm going to take that polyline, that list, and I'm going to add a range of elements right after it, which is going to be all the elements that are all the elements that have been simplified on the right end. Okay, so I'm taking the vertices that are left from the simplification on the left end with the vertices that are left on the simplification of the right end. And let's see if that works. As I do that, you can see that I am getting here I'm starting to get some results. So you can see here that I have simplified because of the value of 32. I have simplified by using only this vertex, and then all the other vertices get simplified. If I reduce this value, I'm probably going to start, you see, all of a sudden, this point and this point are also not simplified anymore. And then, but these points 1, 4, and 6 do get simplified because they're not, their distance to the lines is actually quite small. And as I keep going smaller, you can see that this one doesn't simplify anymore, and this one, and this one. So it's kind of working, all right? You see it working in a very, and here, bam, no simplification whatsoever. However, it's not great, it's not perfect. And if you have a sharp eye on this one, you can see that we're running into a problem here, and the polyline component is actually complaining. You see, zero line segments were collapsed to create a valid polyline. What this means is that if you look at the list of vertices, we're actually outputting a lot of duplicate vertices. What that means is that vertex number 2, this one, is duplicate, vertex number 3 is duplicate, and number 5 is also duplicate. Why is this happen? Well, if you remember, what we just did was, I'm going to take this segment here and I'm going to simplify it. And imagine that it simplifies completely. Like, imagine that it simplifies like in this scenario here, all right? Where all the points on both ends are absolutely simplified. So I'm only left with point 0 and point 2. And imagine that all this stuff also gets absolutely simplified, and I'm only left with vertex 2 and vertex 6. What happens is that here, imagine they all get absolutely simplified. The left simplification has vertex number 0 and vertex number 2, but the right simplification has also vertex number 2 and vertex number 7. You see where the problem is? We are duplicating this vertex on both ends because of this duplicity that because we sent this vertex to both ends of the subdivision. So the only thing that we need to do here is we need to operate a little bit with this right simplified, and then make sure that we do not add here to clean points, we do not add the first vertex of this end. So that is just as simple as saying, for example, avoid duplicating split point. And here what I'm going to say is like, for right simplified, for the points that are coming from the right, for example, I'm going to remove the one that is at position number 0. And as I do that, I can hit here, okay, and then you guys can see that now I am still getting the same result, but I am not getting duplicates. Is that correct? I'm not getting duplicates, I'm not getting any duplicate, I cannot see any duplicates here, and then as I go, whoop, pop, 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 simplification! Yay! Woohoo! All right, this worked. I can't believe this worked. And it only took us an hour and 15 minutes. That's not terrible. Okay, before we wrap up, let's get fancy and let's try doing this with a nicer example. So let me rewrite something here. Complex NURBS curve here on Rhino. I have brought it inside of Grasshopper, and I'm going to subdivide this, for example, in 100. Let me do 200. I'm going to subdivide this in 200 vertices. You see there's... I'm going to plug this into the component that I just created, the list of points. And because it's 0, right now it's not simplifying at all. But you can see that as I start opening this up, you can see how the polyline starts simplifying a lot very fast, you see, and then that one simplifies and this one simplifies and the other one simplifies all the way until I can probably yeah, so let me, okay, and this is a better way of looking at it. So you can see how super cool the vertices on the curve are maintained, because those are the ones that are giving the curve a lot of detail, whereas on the segments that are almost straight lines, then all the vertices are removed. So how awesome is this algorithm? So let me do that again. You see, with a very low value, 0.3, you can see that it's these parts that get oversimplified, but the parts that have a lot of detail stay in. So, and then let me crank this up a little bit. And then here, and then, and then okay, simplification up and simplification. Yay, yay. Woohoo! All right, folks. This was the Douglas-Peucker. Blah, 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 blah. I always forget the name. Sorry. The polyline simplification algorithm. What I would like to finish saying is this implementation that we just did today is not at all the most optimal or the fastest or any sort of thing of that kind. There are other algorithms. There are other ways of implementing the same algorithm that actually do a much better job by using some simplifications. So for example, recursion is a method that is very easy to use and a lot of people consider it very elegant. But depending on where you are working and depending on how many elements or how many consecutive calls to a function you do, you may actually hit a limit. There are certain programming environments where you can only do recursion at like a fixed number of depths. So you cannot call a function itself more than, for example, 32 times. So this is not the case here, but it might happen that you might be working on an environment where you only have limited recursion. So there are other ways of implementing this algorithm that don't really use recursion, that they use infinite loops, while loops until they have all the situation figured out. Also, we did calculate the Euclidean distance between each one of these points and the line. When you're doing distance calculations only because you want to compare those distances between other distances, then it's much more optimal to do what's called the squared distance, which is basically calculating the distance but without doing the square root. The square root is somehow a heavier mathematical computation. So if you can save yourself doing square roots, it's usually a better idea. And in this case, we could have done that because we don't really need the real value. We only need to compare those values against each other. And the two values one will be greater than the other. If one value is greater than the other, the square of those two values will also be greater than the other. So that could have been a simplification. And also, something that we did is that we did compute the linear distance between the point and the line. But if the point had been here, for example, we would have still calculated the distance to this line. Whereas I believe the real algorithm, what it does is that it computes the shortest distance of that point to the segment, which is a slightly different operation. But for the sake of illustration and for the educational purpose, which was what I want to do here, this was an algorithm that I thought was easy enough to implement and break down its logic. So I hope you had fun. And if you like this kind of tutorials, please remember to subscribe, to hit the notification button, and to learn more about geometry operations and geometry gems. Thank you very much.